Hope
Recording is on.
hope you can hear me and this the title slide is visible to you. Anyone?
Yes, sir. Yes.
Okay, thank you. So let's start. So the title is this talk is Introduction to the Quantum Information and Quantum Computing. So in last 2 decades, you must heard about this information thing is going on very rapidly. But how mathematically we deal with the information, how we write it as the mathematical equation that we are seeing today in today's talk. So whatever we see in our physical world, like the communication we are doing right now, our internet, everything we see that these are the all classical information we share with each other. So how we deal with the classical information, how we mathematically write it. So let's suppose a single system. So single system means that it's called as X. So assume that X can be in one of the finite number of classical state at each moment. So what is classical state? So classical state is that describe the moment with uncertainty and error. If you see a die, you can tell the number on die, or if you see a coin, you can say the left and right side of the coin. Okay, so if X is our system, a bit can be a classical system or physical system, then its classical states will be 0 and 1. If we have 6 side die, then we can say the classical state of this die is 1, 2, 3, 4, 5, and 6. If this X is a switch of a fan, then we can probably say the states are high, medium, low, and off. So, but sometimes we don't know the at particular moment when we share the information, we don't know with certainty that the classical state, that system in the particular state. So there might be some probability associated with the system. So for that we have the probabilistic state, and with every state we have a associated probability with it. For example, if X is a bit, then perhaps it is in the classical state of 0 or with probability 3 by 4, and if it is in classical state 1 with probability 1 by 4, then the probabilistic state of X, the classical state, the system being the classical state X equals to 0 is 3 by 4, and the system being in 1 X equals to 1 state, then the probability is 1 by 4. So we have the states now, but how we represent it? So for the representation, there may be many methods, but the simplest and convenience method is if we write it as a column vector. So to how we write the column vector? So this bracket, you can see this is we called as a column vector. So in we have two states in the bit system. So the first entry of this column will correspond to 0, and that second entry that will correspond to 1. So 0 have 3 by 4 probability and 1 have 1 by 4. To construct this vector, we have to see these two things for the classical point of view, that all entries should be non-negative real numbers. So why it is? Because these all are probabilities and probability can't be negative. And the second thing is that the sum of these entries should be 1, because that all the probability, all the possible state have some probability, and the sum of that all the probability is should be equals to 1 or less than it. So sum of this entire vector should be equals to 1. Now there is another notation that we use in our quantum mechanics, which is quite famous, that is Dirac notation. So if you have a classical system that is represented by vector or column vector or a row vector, then we have Dirac notation corresponding to that. So here you can see that this part that is called as cat. So that represents the column vector, and here you can see the row vector that in Dirac notation is represented by this bra. So every vector can express uniquely as a linear combination of standard basis vector. So in the bit flip, you can see 0 and 1 is our standard basis, and we can write this our column vector in standard basis with the probability associated with them. So we have 3 by 4 and 1 by 4 entries in our column vector. So in standard basis, so this is linear combination. This, so 3 by 4 associated with 0 state, and plus 1 by 4 is associated with the 1. So these are the probabilities of being in these states. Now, how do we write this information in quantum perspective? So we took the same idea as we do in the classical mechanics, and we write this in the same as a column vector, but we have to make sure of two things. First is that all the entries are complex numbers, and the second is that absolute square of these entries should be equals to 1. Okay, so same reason that y should be equals to 1, because these all are probabilities, and that should be equals to 1. So if our column vector is their entries are complex, then how we take the absolute square? So this is, here you can see we have a vector v. We take this representation, you can see in two bars. This is called the Euclidean norm. So we take it like this. If all the entries, we do the sum of all the entries of absolute square and take the under root. So this is called the norm of the vector. So that we have to do in our quantum information, quantum representation of the vector. So we have to take this kind of sum. Now these quantum vectors, quantum state vectors, we have represented it in column vector. There all the sum is equals to 1. So therefore it is a unit vector. In classical mechanics, we represent a bit system. So we have 0 and 1 entries, 0 and 1 states. In similarly, in quantum mechanics, we call these bit as a qubits. So the standard basis of these are 0 and 1. These are the example of qubit states, and there is a this plus and minus. This is also example of qubit. Now, why quantum computing? From Ancient times, we are doing computing from abacus to calculator, calculators to computers, and computers to supercomputer clusters. We have achieved so much. But why quantum computing? Because our nature is whatever we see in the physical world is the average out of the quantum nature of the physical world. So whatever we see in the classical world is the average of quantum behaviors we see. So nature is quantum, not classical. Then quantum mechanics provide us a very interesting phenomena such as superposition, entanglement, and that quantum mechanical measurements we do that provide us some extra advantage to do quantum computing. That we use that and we can solve that problem that even classical computers cannot solve. There are some problems that classical computers can't solve, or it will take too much times, years or billion years to solve that problems. Just like as solving that multi electron system, that will take too much time to solve if you take classical computer, but using the quantum computers we can do it very fast and very accurate. Another example can be cryptography and optimization. These are can be use of this quantum computing. So what is superposition? Superposition is when a let's suppose a electron that have one zero and one states. One zero represents that ups, it is in up state, and one represents that it is in down state. So it is in the superposition of that. So in classical mechanics, in classical computing, we have a particular if we put then it is in a particular state. But in quantum mechanics, in quantum computing, it can be simultaneously in the both state, 0 and 1. Next is the entanglement. So what is entanglement? It is a quantum phenomena. There is no representation of entanglement in classical mechanics. So it is a purely quantum mechanical phenomena where two or more particles become correlated in such a way that quantum state of one particle instantaneously affect the another state of another particle. So let's suppose you have uh, two particles A and B, and they are entangled. Now you take an suppose you take B, A and B. So if you take B to take it to another continent, and now you do measurements on A. So B, it will change its state to its respective entanglement state. It will change instantaneously regardless of the distance. Now this phenomena of this entanglement is can't be described by our local variables. So this is a non-local correlations. So if you toss a coin and you can see the rotation, applied torque on that, and you can tell the possibilities of coming head or tail. But in entanglement here, you can't say that you don't have any variables to define it. So this is called that non-local correlations. So here you can see example of this bell. These are this is the bell state. So there are four type of bell state. So one of these I have mentioned here. So this is a entangled state of bit a qubit 0 and 1. Now let's suppose you want to share your information from point A to point B, but when you share this information to using a classical channel, So this information can be copied, or if someone, let's say called C, is there and he copied and broadcasts it. So they can copy it and distribute it. But in quantum mechanics, you can't do that. So that this is not a theorem, like, but it's the property of a quantum mechanics nature. So if you try to copy it, it will be, it will change its state, and you will get to know that yeah, it's has been changed. So this theorem states that it is impossible to create an exact copy of an arbitrary unknown quantum state. Mathematically, if you have a quantum state psi and a blank quantum state 0, there is no unitary transformation used. So we will get to know that what is this unitary transformation in other talks. But suppose for the time being, yes, or the you say it is some kind of operation. So you can't do any operation on the psi to get its a clone while leaving the original state unchanged. So you can't make copy of this quantum information. If you try to it will change the information. Now the another phenomena we have in here is the teleportation. So this is not our sci-fi movie shows that teleportation of materialistic things. It's the teleportation of information. So the transform. Okay, one thing I also want to tell here in no cloning theorem. This is this we use in the key quantum key distribution. So when you want to encode your information in some entangled state or superposition and entangled state and transport it to a position B using the classical channel. So if someone is trying to copy it, that you sender and receiver will get to know that someone is trying to copy it. And this if this process of measurement or copying is irreversible process. So if you tried copying it, you can't back to a original state. So you can't change it. It's a irreversible uh, process. If you tried it, it will destroy its original state and it will change. So now come to the teleportation. So teleportation is that the transformation of quantum information from one location to another without moving physically. It used the quantum principles such as superposition, entanglement as measurements in quantum mechanics. So how we do this teleportation? So for that you need a setup. So setup you required is you need a sender that is called Alice and receiver name is Bob. You need a quantum channel and you need a classical communication channel. So the step one is of your teleportation process is you first prepare a entangled state. So let's prepare. So let's call plus state is a our entangled state of bit. It is a Bell state actually. Now we need a information that we are trying to send. So that is our psi. So psi that is unknown to Alice and Bob that we want to share it. Now we our state unknown state psi that get encoded in entangled state and will be shared to the board. So Alice perform a joint measurement
Okay,
on her.
sorry to interrupt you.
Yes,
Sorry to interrupt you. Go to the first step.
yeah, yeah.
So, entanglement preparation. Out of the four bell states, we can choose anyone, or it's just the customary to choose the basic 100 and kit size
No,
00 and kit size.
anything. anything that is entangled.
Okay, okay.
So Alice performed a joint measurement on her qubit.
So one more small for the no clone state theorem.
Yes. Okay.
Yes. So here is saying one state cannot be replicated a clone. So
Yes.
means it may lose the original state.
Yes.
So can we say it's like uncertainty, like we have the position and momentum uncertainty there. So it's similar
Mhm.
thing. So state itself has uncertainty.
Uh, it will be in the superposition state. So if you measure it, if you try to measure it, uh, it will be in the particular state that will be with the zero uncertainty. So if you are getting, so if you measure, then it will get into a particular state with zero uncertainty.
And
Okay.
sir,
So
how
if you're
different is
measuring twice,
encryption and decryption from quantum no cloning theorem?
Sorry,
How different is encryption and decryption? Because the encryption and decryption, we also do the same thing.
sorry, I didn't get your question.
In cryptography, there is a concept known as encryption and decryption.
Uh,
So using a password or something to encrypt the data. How different it is from no cloning theorem? Well, no cloning theorem tells that you cannot copy a state. For example, you have a hard disk, you can copy a photo into another hard disk, right?
mhm.
So no
Right.
cloning theorem tells that you cannot make a copy at all.
But again, the speaker mentioned that we will get a key or something like that, and then that is the same case in cryptography also.
Uh, no, I mean which key?
Quantum key distribution.
That is quantum key distribution,
That
but
is the
we are not
application
saying
of
that.
this.
Okay, so there are two topics here. He was also talking about, Kuldeep was also talking about teleportation. So teleportation is between two people who are already in a state of entanglement. So you can send one bit of information from one person to another.
So unless until there is a third person involved, we can't share that information beyond those two persons. Is it so?
No, no, no. So the third person involved also should be entangled beforehand.
So
So this is
he or
not a
she should
remote
also
copy.
share the same state with them.
Yes, only if that person has a connection between the others.
They should be intact.
Okay, okay, sir.
So
Okay, sir.
beforehand,
Okay, sir.
it has to happen beforehand. So basically, what happens is initially Alice and Bob meet, they get their states entangled, and then they go to different places. And only after that, this quantum teleportation can take place, not before that.
Okay, sir. Okay, sir.
Yeah.
So after this entanglement process and encoding process, Alice will perform a joint joint measurement on her qubit on her half of the entangled pair plus. And this measurement will result in one of the four possibility outcome of the Bell state, that is 00, 01, 10, and 11. Now what Alice will do, it will share the information of our measured outcome and to the Bob by using the classical communication channel. This measurement outcome tells Bob how to manipulate his part of half entangled pair to reconstruct the original state chart. So based on the measurement outcome, that Bob will perform that some unitary transformation on his qubit, and he will get a original state size. So they this information they are sharing, that is not they are like going to and physically sharing, that is the quantum mechanical phenomena that is changing instantaneously. So they do not need any channel between like air or anything. they will, if you are in another galaxy, that will also happen. They don't need any type of medium between them. So here you see the picture. This is a diagram of this teleportation in the computing process. So with this we will study in next talks. I will give on this particular Qiskit. This is, you can do it in Qiskit, that will can we can do. So but all these phenomena, that quantum mechanical phenomena, that can help you theoretically, obviously, to understand quantum computing and all. But there are some practical challenges also. There like decoherence and error also while constructing the entanglement state. So now that this our quantum computers are not that perfect, but hoping that will be in the future, applying these removing these error in quantum computers, we can achieve that. So that is end of my talk, and these are the references where you can start your this quantum computing uh, journey. And that's with all. Thank you. Any questions you can want to ask?
Yes.
So
Anything?
I just need to know. Can you brief little more about entangled states?
Yes, Ashutosh.
Sir, can you just brief me little more about entangled states?
Only.
How to explain?
Okay. So the idea of entanglement is something like this. Consider a classical particle. We'll go classically. Okay. So consider a small mass, and just as we do it in parabolic or this thing, projectile motion, this small ball splits into two parts and starts moving in opposite directions. Right? Now, one part of this ball reaches you. The other part of the ball is somewhere else. Now, this
Yeah.
particular part of your ball, if you measure its velocity, can you tell the velocity of the other end, other ball? Yes or no?
They're using this
Using
momentum,
classical mechanics.
conservation
Yes?
of momentum.
Yes, sir.
Right. So, the same concept happens in quantum mechanics as well. Instead of this ball splitting into two parts, you can consider something like a gamma ray. Okay. So, this gamma ray undergoes spontaneous combustion, a spontaneous, decay into electron and a positron, antiparticle. So, if you measure the state of this electron, instantly you will know the state of the positron. So, this kind of a relation between two particles or two states is called entanglement. There are various ways of writing it. One of the most simplest ways to write entangled states is Bell states. So, just as you told, you have four different Bell states: 0, 0, plus 1, 1, 0, 0, minus 1, 1, 0, 1, plus 1, 0, and 0, 1, minus 1, 0. These are just
Okay, sir. Okay, sir.
some of them. So you can also have 3 or 4 qubits and so on and so forth.
There are these are the basic,
Simplest
simplest.
basis. Of course,
Okay, sir.
when you have 2 qubits, these are the only 4 completely entangled qubits which are possible. States.
Okay, sir. Okay, sir.
Yeah.
Any other?
Mahavir, Amit,
Did you get anything?
you both are supposed to ask questions. You are as new to this as they are.
I try to keep it very simple without mathematics.
How we make this integral state
Uh,
by splitting the electron.
physically,
Physically. First, we can
Quantum
create
mechanically, how do you do it?
I have
Karthik.
pen and paper. Like I have pen and paper, and I want to create integral state.
So you have 2 different qubits. How do you entangle these two qubits?
So the major fact is that your qubit can be any system. It could be like your
Theoretical. Question is theoretical.
theoretical.
How do you theoretically, if you have two separate qubits, how do you entangle these two qubits? Kuldeep should answer it.
So if they cannot be right if you have two particles and they
Theory.
Theory.
theoretically I'm
What gates do you apply?
okay, that I didn't teach here.
So
Yeah, it's in your diagram also.
yes.
Yeah.
So idea is that on the first qubit you set
So-
up the C0 gate, and then between the first and the second, first qubit acts as the control and the second qubit acts as the target. So you apply the C0 gate, conditional not gate, and then you apply the Hadamard gate. So next talk we will cover the matrices of all these various gates.
basically circuits.
Yes, basically quantum circuits. So there you'll come to know what is C0 and what is Hadamard. All of these can be represented using matrices.
Column vectors and matrices.
Yes. So that is your answer.
I'm not aware of
Next talk.
That's why I'm not telling this gate thing. You got the idea of
So the
entanglement.
next talk, next is
A dense matrix.
Ashutosh, Sonam, and whole gang. What do you want me to cover? I'll be giving the next talk on this Saturday or Monday. Let us see when. Okay, is Saturday all right?
Saturday is all right, sir.
For you,
Yes,
okay,
sir.
Ashutosh? Sonam?
Yeah, it's fine. It's fine.
Sure?
For
Okay.
Abhida also, it's fine.
Okay. So we'll have a talk on Saturday. So what do you want me to cover? One
Sir,
request is
with quantum circuits, but with little bit maths also, sir.
sure. Okay. Fine.
With
Mathematics.
mathematics. Okay.
Yeah, same thing from the basics, sir.
Sorry?
The quantum circuits only from
Very
slightly
basic.
from the basics.
Yeah, sure. I'll go with the gates, introduction to quantum gates, how they are different from classical gates, and then
Okay.
we'll go ahead.
Yes, sir.
Okay. HG will give eventually. We'll go there later. All right then. Any more questions?
I have read about it.
Say-
How we create
No,
the
sir.
like
One second.
No,
Ashutosh.
to entangle particles physically, like entangling two photons like that
Okay.
thing. So the Chinese, they have entangled some big particles like that. How did they do it? Are they entangled? I actually read only of entangling photons kind of particles, very small particles, but they have entangled some big particles. And then they put one in their space
Satellite.
using satellites. And
Yeah,
one in there.
it's quite old news.
Yeah, it's of
around
2020 to 21, 22.
before that. Before COVID.
Yes.
Yeah, during the period of COVID. Actually, it's
So
already.
sometime we can even cover that.
Practical aspects of this.
Correct.
We can.
And this one is called as spooky action or spooky.
Correct.
is-
So that is basically entanglement. Spooky action
Yeah,
at a
paradox.
distance.
These EPI paradox and all.
So one more thing about entanglement and teleportation. Even though the action takes place at a distance, we cannot have any sort of communication. For example, once the teleportation is complete, that is, once Alice measures her state, she has to find the classical means of communication and inform Bob that she has completed her measurement. Only after that, Bob can perform his measurement and the teleportation is complete. So until Alice communicates to Bob, using classical, ways of communication, nothing can happen. So even though all this action is instantaneous, it still does not violate the basic laws of physics that information cannot be transferred faster than the speed of light. It is always slower than the speed of light.
See, so I got a question. What are the practical application that it can have then? if it is not just speeding the transfer of you can select memory information,
That's a good question. So,
can it
you
have
want to
some
try?
practical application?
Kuldeep first, then Karthik.
So I mentioned that our nature is a quantum, not a classical. So if you suppose you have many electron systems, so what we do in the many when we try to solve this, what we do? Well, we do the average thing and we try to predict the behavior of the many particles. But in quantum mechanics, this quantum computing, we can uh, do this entanglement thing with the electrons and we can calculate. So these in this process we can have more information about the system.
You want to say add something, Karthik?
Yeah, I want to say in this direction only that you cannot obviously transfer information faster than the speed of light, but like let's say it can help you. What I think is in your approximations, the current approximations which you make, you have to study the full system, right? From this end to that end. But let's say, for example, this end and that end are basically entangled to each other. So by studying only the one end, you can get information also about the other end. So your time will save by
Or this using this no cloning theorem, you can share encrypted things that nobody can copy. If they will try to copy it, that information will be destroyed.
Good.
So if you want to share the like some military information, and so if another country will steal it, so to prevent that, we can use quantum computing to share this. Or in this financial system, so there will be very helpful. Or do you heard of this key distribution of and crypto? All of
encryption क्या क्यों जो लोग शेयर करते हैं
Quantum
5
key
6
distribution.
7 से इस टाइप का क्या कहते हैं उसको encryption code.
Yes, key
That is-
distribution and yes. So before I say anything, Ashutosh, you had something to ask?
No, sir. No, sir.
Okay. So apart from these two things, it's also a lot more things. For example, now if you're trying to solve helium atom, okay, hydrogen atom is very simple. It is the simplest system, two-body problem, and you can solve it exactly using analytical methods. Now consider helium atom. You have a nucleus, you have two electrons. So if you want to solve, basically get the trajectory of the electron around the nucleus, that is solving, right? It's a three-body problem. Can you do it? No.
It's very tough.
Exactly. So what do? You take various approximations, Hartree-Fock approximation, something else, various other approximations, and solve it. Correct? Now, consider quantum computing. It is basically using quantum mechanics to do things, right? So, these kind of processes are very easy to do in quantum computing. So, your entire Hartree-Fock method can be encoded in a circuit and you can run it. Classically, what takes much longer becomes very fast using quantum computing.
So you mean to say then you can solve uranium
You cannot solve an electron problem
multi-electron.
accurately. You will still have uncertainty, but you can solve it faster and more efficiently. So, why no cloning theorem can be used to share information is basically that if you have information being shared over air, radio waves or whatever, you have to do some mathematics to encrypt this information, correct? So, in quantum mechanics, what happens is it is not the mathematics that is stopping you, it is the physics that is stopping you. So, it is physically and quite literally physically impossible to copy that information. So, it is stored between two states.
One day I was thinking, since entanglement allows us to if you change the configuration of one particle there, configuration there changes.
Correct.
So there can be some other way like this. spooky action that can
That
be
is spooky action at a
yeah,
distance.
there can be some other kind of phenomena like that other than that can be similar. This much speed.
Improve the speed.
Yeah. See, we know the speed of light is limits.
That's the problem. Okay, so let's say I have a qubit and you have a qubit. Okay, and these two qubits are entangled. Mine is in one state, yours is in the opposite state, or whatever state. So now I change the state of my qubit. How will you know that I have changed the state of my qubit? You cannot.
Yeah.
So until you perform a measurement, you do not know the state of your qubit. Therefore, it does not matter what I do to my qubit and what happens to your qubit, you will not know. The state of the qubit will have changed, but you will not know it. The only way to do it is measure it. And the question comes, when will you measure it? And how will you know I have changed my qubit?
Yeah.
So this information between us has to be shared classically. And that will happen only at the speed of light, at fastest. So I can just send you a light signal and it will happen at the speed of light, that communication. So therefore you cannot beat the speed of light. That is impossible. Again, fundamental laws of physics. You cannot send information faster than the speed of light.
So if Alice is on Earth and Bob is on Mars, and we have some communication between Alice and Bob, and if Alice changes some information or some state, and she wants to send the information about the changes. So if she send that information classically and tells that yeah, I have changed. So how Bob will see the changes? And this so distance is the thing that when
Bob do the measurement.
is there any limitation?
No, there is no limitation with the distance. So this change in the Q states happens instantaneously. It doesn't matter whether Bob is on Mars, Andromeda, or the farthest galaxy with known to man. It doesn't matter. It will happen instantly. But this information needs to be communicated that yes, I have done something. See at your end.
So that is completely independent thing.
Yes,
But
yes.
I'm sharing that I've changed.
Yes, that is entirely independent. That's a separate means of communication, and that cannot be using entanglement.
Still, my question, I have a confusion that how this system is changing.
Yeah.
This
Still now, is there any physical
Yes. So basically, it is the basic quantum mechanics, right? Pauli's exclusion principle. No two particles can have the same state. So these two states cannot be in the, cannot
exist in the
same state.
But
There are limited number of states available for them to exist. So if one is in one state, the other has to be zero. So if I flip this to zero, instantly because of this principle, Pauli's exclusion principle, that will flip back to one.
You can use that this information that this change is done there, then that will also change. This information is something which is not basically traveling. This information is already there from the start. So when Alice was on Earth and this Bob was leaving for Mars, at that time only, when these states were entangled to each other, this information remained that when you will change, I will change.
but there's no interaction.
No interaction,
interaction
because the
with
information is always there. No,
because they are in
information is not traveling at all. It was always there.
Like in Pauli's principle, what happens that there are some interactions. Okay.
There is no interaction, not even in Pauli's
Like
exclusion principle.
electrons.
There is no interaction. It is just that no two particles can exist in the same state. That's all it is.
And if I hit one of the two electrons,
Huh? You can eat it, hit it, break it, do whatever you want.
say one electron, if I say the by Pauli exclusion principle, one is having upper spin and the other one is having
Yeah, it is still recorded.
one is having clockwise spin and the other one is having anti-clockwise spin.
Wrong concept of spin. Anyway, are we boring you guys?
Yes.
No, sir.
Yes or no?
I heard no.
Okay. Well, the talk is over. This will be just a discussion. feel free to join in, or if you're busy, you can also leave, no problem. Yeah, so spin of an electron is a mathematical construct.
Yeah.
It doesn't spin.
Yeah. Yeah.
No
I've heard about
clockwise,
it,
no
but
anti-clockwise.
Uh,
When you say up spin, mathematical. When you say down spin, mathematical. There is nothing up, nothing down.
yeah.
Okay?
Uh,
Yeah. Now you can ask your question.
yeah. Say if one is having two entangled particle, one is having up spin, but the another one is having down spin.
Yes.
If I destroy one,
Well, if
happens to the other?
you destroy the particle, entanglement will also get destroyed. That's all will happen.
So the other
It
one
will
will
continue
take
to
a
exist.
random spin. It can have up spin. It can have.
That depends on what happens during your destruction. If you want to go that deep,
Okay.
so how you destroy, what happens to it, if it's changed, if its
Destroy-
state changes while destroying.
Destroying is also a measurement. So
Destroying a state is a measurement. Destroying a particle, I do not know.
What do you mean by destroying the particle?
Let's say you make it interact with the positron. So the particle no longer exists.
Electron positron.
So the state no longer exists. So the entanglement is broken.
Yeah. It may change the other one's spin, or
It may or may not use. May or not.
So Pauli's exclusion principle is well.
Yes. Yes.
That's why it is possible.
Yeah.
it's 1 hour.
It is like particles.
Slightly more than an hour.
They space here.
I got one more question. If two electrons are inside the atom, then we can say I have applied Pauli exclusion principle, whatever that quantum states are only inside the atoms. Principle, quantum number, principle, all that thing. But if we say like Alice and Bob, they are far apart. So is all the thing around us that's the quantum state? Is this room a quantum state? If I put one electron, one whatever that particle is, and the one is there, can we say that this room is a quantum state kind of thing?
Yeah, as I said, quantum state is not defined to anything. You can take anything your quantum state.
It can be of a very big size, or it can be of very small size also.
It is.
Size does not like if you have single atom. So and you are calculating the spin of one electron in that single atom. You are using that as your quantum state. You are free to do that. If you take a let's say this, let's say you take C60 and you take some particle inside it, you can take that spin also, and that also you can define a state. Next, you can take this full room. Inside this room, there's one single atom or something like that. That also you can take as your state. So it's not limited to that. You can, if you do not want to take particles, or you do not want to take mass particles, take photons. That can also be a quantum state.
So this nitrogen inside C60 it used to create qubits. So
Yeah.
So
Quantum dots kind of thing. Yeah, I've read.
using that also we can create a superposition state.
The reason why you are sitting on that chair is also quantum mechanics. Sure, you can write a state for that. You can solve it if you have the patience to solve the huge equations and the integrals. But yes, absolutely. Okay, shall we wind up?
Yes.
It confuses a lot. We just is there a marker?
Okay then, Amritesh, bye bye. We'll stop the talk here. See you.
Well,
This is all.